What we have done here is we have taken three examples. This is example 1, this is example 2, this is example 3, and all of these signals are cos 2 pi FDN, cos 2 pi FDN, cos 2 pi FDN. So these are three discrete time sinusoids, and their first 10 values, first 11 values, the n is given as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are first 11 values of n. The values of the sinusoid are calculated. So in this example, we have FD as 1 upon 3, which is a rational number. And when we place the values of FD and n into this expression, the numbers of the signal come back as 1, minus 0.5, minus 0.5, and then they repeat themselves as 1, minus 0.5, minus 0.5, then again 1, minus 0.5, minus 0.5, and so on. So we see that this sinusoid, discrete time sinusoid, is a periodic function, and the periodicity is coming back as 3, which you can see is the denominator of this FD as well. FD, we noticed, is equal to K upon N. Capital N is a periodicity. Now in example 2, everything is the same except FD is now 3 upon 7, which again is a rational number. So with 3 upon 7, the values come out to be 1, minus 0.9, 0.6, minus 0.2, minus 0.2, 0.6, minus 0.9, and then they start repeating themselves as 1, minus 0.9, 0.6, minus 0.2, and so on. So the periodicity is 1, 2, 3, 4, 5, 6, 7, and here the denominator is 7 as well. So this signal is also periodic, and we see that the frequency is a rational number. Now in example 3, we take an irrational number as a frequency FD, square root 2. So when we place square root 2 in FD and choose n as 0, 1, 2, 3, the numbers come out to be 1, minus 0.9, 0.5, 0, minus 0.6, and so on. And although I have stopped at 10, you can carry on, and you will find that there is no periodicity. Although this is a periodic function, cosine happens to be a periodic function in continuous time, but in discrete time, postulate 1 is indicating us that in order to check for periodicity, we will have to keep an eye on the frequency FD. If FD is a rational number, only then this will be a periodic function, otherwise it will not be a periodic function. This is an important observation which will be used and come back to us in various different topics in this course. So this is something to remember. Now these three signals are the same signals which we just looked at in the numeric format. These are the plots, and you can see that the periodicity is very clear here. The periodicity is very clear here as well. After 7 samples, the signal repeats itself every 7 samples. And here, when the frequency is square root 2, there is no periodicity. You can keep on looking, there is no periodicity. Okay, now let's look at postulate 2. Remember, in continuous time sinusoids, the postulate 2 was that a continuous time sinusoid with a different frequency will always generate a distinct signal. Now here it says that discrete time sinusoids whose frequencies are separated by an integer multiple of 2 pi are identical. Now for a second we forget what this integer multiple of 2 pi is, but in simple terms this postulate is saying that discrete time sinusoid with two different frequencies can be identical. Now this is something very different from what we are used to of we know that if you change the frequency, the signal changes its shape. But here we are seeing that the postulate is claiming that it is possible to have identical waveforms coming from two different frequencies. Now let us look at what this integer multiple of 2 pi means and how the discrete time sinusoids of such frequencies become identical. So to consider, to evaluate this, we consider and start with the same cos 2 pi fdn expression, which is a simple discrete time cosine. And what we do, that we add, here we have fd, and here what we do is add an integer value with the frequency. So, and this integer value k can be 0, 1, 2, or -4 or -5. So if we compare this expression with this expression, we see that the frequencies of the two expressions are separated by an integer multiple of 2 pi, and that's what this term means, that the frequency of this expression and the frequency of this expression are distinct by an integer multiple of 2 pi. Now let's the more important thing is to see whether when we have this frequency fd plus k and we draw the signal, does it give us a different signal, or do we get back this original signal? So we start with this cos 2 pi fd plus k into n expression, the right hand side of the expression, and we use cos alpha plus beta expression as cos alpha cos beta minus sin alpha sin beta, and we expand this expression, which is now simplified into cos 2 pi fdn into cos 2 pi kn minus sin 2 pi fdn and sin 2 pi k into n. Now we know that k, small k, is an integer and small n is an integer. Whatever the value of k, whatever the value of n, they will be integer, and multiple of two integers will always be an integer, thus making cos 2 pi into an integer as equals to 1. So this is now 1, and similarly here k into n will be an integer, and sin 2 pi k into n will become 0, thus making this entire expression as 0. So this becomes 1 and this entire expression becomes 0, which leave us with cos 2 pi fdn. So this is the proof for the second postulate, which says that discrete time sinusoids whose frequencies are separated by an integer multiple of 2 pi are identical. This is again a very important observation. We do not expect this in continuous time, but we are seeing this in discrete time. So when we will work in discrete time domain, we will be having trouble in identifying correct frequencies if we are ending up with the same signals. So let's look at an example. This is a similar example as we have seen in postulate 1, but here everything is same. What is different is that in example 1 I have chosen fd as 1 over 6. In example 2 I have chosen fd as 7 over 6, which is which is separated from the first example by an integer 1. And in example 3 we have fd as equal to 13 by 6, which is separated by 2 with the original fd. And when we compute the signal values of all three examples, we find that 1 0.5 minus 0.5 minus 1 minus 0.5. Similarly the second example, if you look the values, and the third example, if you look at the values, all these three examples are giving us back the same signal values. So in case at you are provided with with values of 1, 0.5, minus 0.5, minus 1, minus 0.5, 0.5, 1, and so on, and you are asked what will be the frequency of the signal, the entire cohort cannot come back to me and say this is 1 over 6, because the same values can come back from 7 over 6, and the same values can come back from 13 over 6, and so on and so forth. So this is a big problem, and we will look at how to solve the issue. The graphical format of this example is given here. You can see that the first example is 1 over 6, the second is 7 over 6, the third is 13 over 6, and you look at the waveforms of these three signals, they are identical.